So let's read the scientific paper on the GraphCast that was mentioned in the last podcast. This is they published a paper in Science on this, as we mentioned in the previous podcast. It says learning skillful medium range global weather forecasting. Global medium range weather forecasting is critical to decision making across many social and economic domains. So you probably know short, medium and extended range scales. 1 to 3 days is typically short range, and medium range is days 3 to 10. Extended range is typically beyond week 2. Global medium range weather forecasting is critical to decision making across many social and economic domains. Traditional numerical weather prediction uses increased compute resources to improve forecast accuracy, but does not directly use historical weather data to improve the underlying model. So you rely on a first principle model, you initialize it, you integrate forward. You don't really care about past weather, except some people do so-called analog forecasting, where you have a table of past weather events and then you look at forecasts and try to fit them into past patterns. So it's not direct use of weather from the past, but trying to make blended model and past weather forecasts. I hope that's clear. So here we introduce GraphCast, a machine learning based method trained directly from reanalysis data, predicts hundreds of weather variables over 10 days at 0.25 degree resolution globally in under 1 minute. Global 10-day forecasts at 25 kilometers in under 1 minute. You probably don't even, if you're not a weather forecaster or a global modeler and so on, you don't even realize how revolutionary that is. GraphCast significantly outperforms the most accurate operational deterministic systems on 90% of the 1380 verification targets, and its forecasts support better severe event prediction, including tropical cyclone tracking, atmospheric rivers, and extreme temperatures. GraphCast is a key advance in accurate and efficient weather forecasting and helps realize the promise of machine learning for modeling complex dynamical systems. If you're not aware of these terminologies, deterministic means there is just one realization. You integrate once and you say that's the forecast. When you say probabilistic, you have multiple integrations and then you look at the range by perturbing the initial conditions in various ways and so on and so forth. And the other technical term here is atmospheric river, for example, which just means places like California get lots of water vapor coming in predictable ways from the west, so you can literally see them coming, and if you can predict those, then you have a good chance of predicting mountain snow, rainfall, and so on and so forth. GraphCast, how does it work? Very briefly, here we've introduced a machine learning based weather prediction as opposed to numerical weather prediction approach for global medium range weather forecasting called GraphCast, which produces an accurate 10-day forecast in under a minute on a single Google Cloud TPU v4 device. You can go figure out what that is, and supports applications including predicting tropical cyclone tracks, atmospheric rivers, and extreme temperatures. GraphCast takes as input the two most recent states of Earth's weather, the current time and 6 hours earlier, and predicts the next state of the weather 6 hours ahead. Single weather state is represented by a 0.25 degree latitude longitude grid, which is equivalent to 721 by 1440 grids, which corresponds to roughly 28 by 28 kilometer resolution at the equator. So approximately 25 kilometers across the globe, where each grid point represents a set of surface and atmospheric variables listed in table 1. Like traditional numerical weather prediction systems, GraphCast is auto-regressive. It can be rolled out by feeding its own predictions back in as input. So you integrate, then you integrate forward by using the past integration and so on to generate an arbitrarily long trajectory of weather states, as we will see here. I won't read all these details because I just want to give you a sense of what's happening with AI. So here is the input weather states, global weather state, global 0.25 degrees, and GraphCast does its magic with that, and it predicts the next state, and then GraphCast keeps on basically bootstrapping forward and can keep going for next many 6-hour steps. So that's kind of revolutionary in terms of how quickly you can produce 10-day forecasts in a minute, under a minute, right? So you have various things here like encoder, processor, decoder, and then simultaneous multi-mesh message passing, which is artificial intelligence, deep mind, GraphCast learning. So I'm just using words, but you can see how it works. You can read the details in the long caption here. I'm skipping it on purpose because my goal is not to explain the technical details, because I'm not an expert on GraphCast or AI, so I'm just trying to give you a sense. Just to look at some examples, typically they look at some high resolution systems, forecast systems, and compare to GraphCast and look at typically RMS errors in terms of 500 millibar geopotential height meter squared per second square. This is normalized root mean square error difference. So that's a skill score. You can see the lower the better. So for lead time of few days, GraphCast is doing, the high resolution dynamic model is here, so the GraphCast is here, much better. And skill score in terms of lead time versus correlations against observations, GraphCast remains good and comparable to dynamical forecasting, and then dynamical forecasting drops off faster than the GraphCast does here in terms of correlations. Okay, so here higher is better in terms of skill scores. And then other ways of looking scorecards at various levels, and this is here looking at zonal winds, mean sea level going up in altitude and lead time, and so on and so forth. I think it's looking at zonal winds, meridional winds, geopotential height, temperature, I think, and humidity, and so on. There is a cyclone tracking example. Again, errors are lower for GraphCast, atmospheric river errors are lower, cyclone tracking, paired analysis much better than the models and numerical models, and extreme heat precision recall also much better than the precision is much higher for GraphCast. Are you convinced? Well, it should be reliable because it's published in Science after all, right? So what are the conclusions? GraphCast's forecast skill and efficiency compared to HRES shows machine learning based weather prediction methods are now competitive with traditional weather forecasting methods. Additionally, GraphCast's performance on severe event forecasting, which it was not directly trained for, demonstrates its robustness and potential for downstream value. We believe this marks a turning point in weather forecasting, which helps open new avenues to strengthen the breadth of weather-dependent decision-making by individuals and industries by making cheap predictions more accurate, more accessible, and suitable for specific applications. With 36.7 million parameters, GraphCast is a relatively small model by modern ML standards, chosen to keep the memory footprint tractable. And while HRES is released on 0.1 degree resolution, 137 levels in the vertical, and up to 1 hour time steps, GraphCast operated on 0.25 degree latitude longitude resolution, 37 vertical levels, and 6 hour time steps, so much faster in terms of the integration. This time step in a numerical model is a stability thing. If you use a large time step, it will go crazy because of the way numerical integration works. Errors can grow, you can get crazy waves and so on, but in AI you don't have that problem. So 6-hour time step works because of the Era 5 training data's native 0.25 degree resolution. GraphCast is running at that resolution, and engineering challenges in fitting higher resolution data on hardware make it harder to go down to 0.1 degree and so on. Generally, GraphCast should be viewed as a family of models, with the current version being the largest we can practically fit under current engineering constraints, but which have potential to scale up much further in the future with greater compute resources and higher resolution data. One key limitation of our approach is in how uncertainty is handled. We focused on deterministic forecasts, which means one integration, which is typically not the way you do things, because Mother Nature goes in many possible ways as it goes forward from now, and models have to cover the range of possibilities, so you typically do multiple realizations. So compared against HRES, the other pillars of ECMWF's forecast system, the ensemble forecasting system ENS is especially important for quantifying the probability of extreme events, and as the skill of the forecast decreases at longer lead times. So basically GraphCast has to match all those things to be better than the dynamical model. The nonlinearity of weather dynamics means there is increasing uncertainty at longer lead times, which is not well captured by a single deterministic forecast. Ensemble systems addresses this by generating multiple stochastic forecasts which approximate a predictive distribution over future weather. However, generating multiple forecasts is also expensive, and we don't always know how many ensemble members, how many integrations you need to capture the potential evolution in the real world. Okay, so by contrast, GraphCast's MSE training objective encourages it to spatially blur its predictions in the presence of uncertainty, which may not be desirable for some applications where knowing the tail or joint probabilities of events is important. Technical things, I won't go into it, but basically you have extreme events possible, and deterministic forecast is almost guaranteed to miss it, so you need to have a range of probabilistic forecasts. Building probabilistic forecasts that model uncertainty more explicitly along the lines of ensemble forecasts is a crucial next step for GraphCast. It's important to emphasize that data-driven MLWP relies critically on large quantities of data and their quality, which is in the case of models trained on reanalysis, depends on the fidelity of the numerical weather predictions. Therefore, rich high-quality data sources like ECMWF's Mars archive are invaluable for training GraphCast. Our approach should not be regarded as a replacement for traditional weather forecasting methods, which have been developed for decades, rigorously tested in many real-world contexts, and offer many features we have not yet explored with GraphCast. Rather, our work should be interpreted as evidence that MLWP is able to meet the challenges of real-world forecasting problems, and has the potential to complement and improve the current best methods. Beyond weather forecasting, GraphCast can open new directions for other important geospatio-temporal forecasting problems, including climate and ecology, energy, agriculture, and human and biological activity, as well as other complex dynamical systems. We believe that learned simulators trained on rich real-world data will be crucial in advancing the role of machine learning in the physical sciences. So let's leave this here, and in the next podcast we'll read off one more paper which is on neural general circulation models for weather and climate, which is also AI approach. Okay, let's meet in the next podcast then.